So, all right, so we're up to chapter 8. We skipped a few chapters because I think debugging is much easier than disassembling. So, a disassembler takes apart the program and shows you the executable assembly language instructions, and then you have to read them and figure out what they're doing. And that is pretty difficult for people. Debuggers are much more fun, like dynamic analysis. You're just running it and seeing what it does, and you can stop it and change the way it runs at any point. So there's two very popular debuggers. Ollie Debug is a real old classic used for Windows people to cheat on games and stuff. It's fun and easy to use. IDA Pro is a disassembler, and it has some limited debugging feature, but almost nobody uses it. It's not much fun to use. WinDebug is what the Microsoft uses internally, and it supports all the advanced debugging features, but it is quite difficult to use. It's really essentially a command line tool instead of a GUI tool. So we're going to start with Ollie and then move to WinDebug later when we have to debug the kernel, because you cannot debug the kernel with Ollie Debug, and you can debug the kernel with WinDebug, which is what we're going to do when you do a kernel mode rootkit. Anyway, if you turn on, whoa, something bad. Okay, so let me go back. I've somehow skipped stuff. All right, so those are the debuggers. All right, so the source level debugger is what a software developer would use. You make software, you compile it with symbols, with a special flag when you're compiling it, and then you load it in a debugger, and then you can see your source code in C or Visual Basic or whatever it is, and you can debug it step by step, and you can print out the values of variables and so on while your program runs and find out what the problem is with it. And that's what developers do. But malware analysts do not have access to the source code, and typically they don't have the symbols in the executable to make it difficult. So you have to use assembly code, and you don't have the names of the variables or the names of the functions, and so it gets pretty confusing. All right. Now, another thing that you often see is when an app crashes, Windows will pop up a message saying this program has stopped working, and you can debug the program here. But it will tell you some information. It will tell you the name of the module that failed and some codes and sometimes some addresses, a little bit of information here. And if you debug it, it will then look to see if you have a local debugger installed and open it in the debugger, which is often WinDebug. So that's one way to go. And this points out one important issue is the crash dump. You can configure your Windows machine to save a crash dump, which is either a part of memory or all of memory saved in a file when a program crashes, and then that can be analyzed later. And the main use of this is people who pay Microsoft, they pay for a support contract for their Windows at companies. Then when a program crashes, they take the crash dump and they send it to Microsoft, and Microsoft will analyze it with WinDebug at that end and figure out what the problem is, and then give you a hot fix or something to patch the problem. And that's what essentially all of the Microsoft knowledge base articles are. They are the end result of trouble tickets where somebody had something crash and they sent all the data to Microsoft and they figured it out and got a solution, and then they publish it up in one of those articles so other people can refer to it. Anyway, so, all right, the two big types of bugging, first there's source code and without the source code. And for us, it's almost always without the source code. And then there's kernel versus user mode debugging. So remember, in the hardware of a machine, there are 4 rings in the processor, 0, 1, 2, and 3. 0 is the most powerful. That's the kernel that can access the hardware directly. 1 and 2 are not used by any modern operating system. And 3 is where all the user mode programs run, like your browser and Microsoft Word and everything else you launch. And you don't have the privilege to use all these machine language instructions from user mode. If you want to access the hardware, you can't do it directly. All you can do is call kernel API calls, which use code written by the operating system designer, Microsoft in our case. You can only do what Microsoft wants you to do, and you can only do it the way Microsoft allows you to do it. Anyway, so that's the problem. Now your debugger is running on the same system, and it's an executable. So it's the operating system separates your debugger from other programs. So if you want to do kernel mode debugging, then you've got a problem. Now, user mode debugging, like Ollie Debug, is simple. Ollie is just an application. It just connects to another application that's running. It controls it with breakpoints, which we'll talk about. So it's really very simple. But if the operating system was to crash, if something was wrong with the kernel, then Ollie would die and the other program would die. And it doesn't have the authority to stop the kernel. It's in user mode, and it's not powerful enough to stop the kernel. This is why a user mode program like that, debug, can't debug the kernel. Now, if you want to debug the kernel, this is actually kind of crazy. Suppose you wanted to put a breakpoint in the kernel and stop the kernel processing. Then your machine would be frozen. It would no longer receive input from the mouse to the keyboard or anything. So how can you do it? It's like sawing off the branch you're sitting on. So the old-fashioned way to do it was you had to have two computers connected with a serial cable. You'd now have a master and a slave computer, and the one you're debugging would be controlled by another. You'd run WinDebug on the other computer. It would then put a breakpoint on this machine, which would stop, and then you could examine the memory from the other machine. And this is a really old system. It was inconvenient and difficult to set up, especially since nobody had the old serial cards anymore. It was really designed for these old serial cards that don't exist on modern machines. So there was a market to make USB serial converters, but they didn't work very well unless you paid $300 for them. And anyway, it was pretty much a mess. That was the old way. But what you would do is connect two machines by these serial cables. Then you would set one of the machines to debugging mode down here. You press F8 during startup, you press boot up, you then go to debugging mode. Now, after you do this, the break key on the keyboard, which is equal to the print screen key, will cause the blue screen of death. It will freeze the kernel. So I did this in a lab. I had students doing this, and other students were trying to do projects and get screenshots. And every time they hit print screen key, they get the blue screen of death and lose their screenshot. So this was not popular. Technically, if you use shift print screen for print screen and the break key without the shift key to break, you could do it. But overall, this was a mess, and my students suffered greatly. And I finally was saved by Mark Russinovich. Mark Russinovich is extremely wonderful. He understands Windows internals better than anybody. He made these sysinternals tools, and one of them is the LiveKD tool, and this is what we're going to do, which is so much better. LiveKD is a brilliant tool because Mark Russinovich figured out that you could make a crash dump of the kernel, and you could connect the debugger to the dump. And it won't be able to actually run the code or put in a breakpoint, but it will be able to see the code, and you can do a lot of what you need to do for kernel debugging with only one machine. Because all you do is make a dump and then look at the dump. So you can take sort of a snapshot and examine what the kernel is doing, and that turns out to be enough to get quite a lot done, and that's what we're going to do. So I ought to mention this. Talk by Joe McCrae from B-Sides, Rhode Island is fantastic. He explains exploit development for mere mortals, and this is why I wrote the CNIT 127 class. I've been trying to do exploit development for years, and I couldn't get it to work. And then Joe McCrae's video showed that it was pretty easy to do some simple things with debug, and his student, Georgia Weidman, wrote a book that has a very good explanation of how to do buffer overflow in one of the appendices. And that talk and that book made it possible for me to get over the hump and get my my exploit development stuff working. So I highly recommend, if you read that talk, that's cool. I thought it was very inspiring. This is fantastic. That's why I made my exploit development class. So Joe is great. I know Joe, I've been friends with him for years. He's really doing the same thing I'm doing. He's trying to take this complicated stuff and make it easy for beginners to get into it. And he's very successful. So anyway, so I've got some cahoots about this stuff. Let's bring them up. It is 8A. Yeah, I almost never watch hour-long talks. That's one of the few I've actually watched. Joe is very good. Georgia Weidman's book is very good too. We're using it for CNIT 124. I read other books like The Gray Hat Hacking, and they're all too difficult, and they're using versions of everything that are too old. So Joe's stuff and Georgia Weidman's stuff are simple and up to date. It makes a huge difference when you're a beginner and you get stuck on every little problem. All right, give it a few more seconds. All right. All right, so what technique requires two computers connected together? Okay, that's kernel mode debugging. All right. All right, what technique is almost never used by malware analysts? Source code, we typically do not have the source code. That would be too easy. All right. All right, what technique displays assembly code but does not allow you to run it? Okay, that's disassembly. Disassembly just lets you see the code, but you can't run it. All right. All right, if a crash causes the blue screen of death, what should you do? That's the kernel mode crash. That's why you see the blue screen. If the kernel crashes, the computer cannot recover and go on. If an application crashes, the kernel is still running, so it can pop up a message and keep running the other applications. But if the kernel goes down, your computer is toast. So, right, we got 3 for Juarez. Gene. Ollie. Ollie will have to tell me who he is. Juarez, I remember, I think. And all right. Ollie, okay, good. All right. I gotcha. Whoops. There, okay, good. All right. So let's go back and do another section of this stuff. Okay. So when you use a debugger, you can start the debugger first and then launch the program in the debugger. Like you might open a Microsoft Word document after you start launching Word first, and then it will load the program in memory and stop. It will not run. It will load it and get ready to go and stop dead because presumably the reason you're using a debugger is you want to examine or change something about the program. Or you can have a program already running and you can attach it to a program that's running. It'll attach to the running process. In either case, once you connect the debugger, the program stops. This is by design, so you can modify something and control the stepping through it, but it does confuse people at first because you're trying to do something and you debug a program and it's no longer listening on a network port or doing whatever it's supposed to do, not unless you start it again inside the debugger. Now you can single step through the assembly language instructions. You can do that, but of course it takes thousands or millions of assembly language instructions to get anything done. So this is only going to work if you're close to whatever the action you're looking for is. In that Jasmine program, you have simple programs that only have like 10 or 20 commands, so you can single step through them, and that's fine. But in a real program, you have to first find the area of interest, and then you might single step through it. So here's an example from the book. It's going to move this word from this memory location into EDI. then move in a value, and it's going to XOR with a fixed value. This is doing the same thing that my Jasmine program did. This is taking data from a location in memory, and it's taking a fixed value and XORing a word with it, and then it's incrementing it. And I guess it's going through it byte by byte in this case. So it's XORing this byte, incrementing it, and then looping back to here. So it's going to loop through byte by byte and XOR all the bytes with this fixed value of 9C. So here you see there was unprintable junk here, and it goes through the bytes one by one, and it turns them into printable, readable strings. So this is a very common technique to conceal strings from a malware analyst, where if they first run strings on it, they're going to see nothing but this unprintable junk. But when the program runs, it will do the XOR, make it readable, use it, and it will only be present in memory while the program is running, and perhaps even only for a brief period of time while the program is running. So when you are stepping through something in a debugger and you hit a call that calls a subroutine, you now have two ways to debug. One is to step into. Then it will go into the subroutine and stop, and now you can go step, step, step through the subroutine. Now, sometimes you want to do that, but often you do not want to do that because you're often reading code that's written by the developer, and you want to find that. And then it goes a system call into the kernel, like a print. Now, you probably don't want to debug the Microsoft kernel. Most of us are trying to understand the malware that's out here running in userland. And when it makes an API call to Microsoft, I'm not interested in seeing what happens inside that API call. I'm willing to accept that the Microsoft code is probably good, and I just want it to finish doing the call and return, and then go to the next step of the high level I'm in. So that's called a step over. A step over will go into the subroutine and do everything that subroutine does, and then come back and then stop again. So you stay at the high level where you are. So you have to be aware of that. Of course, this means if something crashes in the subroutine, it won't come back. And if something important happens in the subroutine, you might see it. So, sometimes you want one, sometimes you want the other. Anyway, that's the difference between stepping over and stepping into. And then there's breakpoints. You can put a breakpoint in a program. We're going to do this later with Ollie Debug. And then you just let it run until it hits the breakpoint. And then you can zip through all the code that you're not interested in and stop at the part you're interested in and examine that carefully, and then zip to the next spot. And that's why this is so much easier than using a disassembler where you just have all the code and it's not easy to find what part you should be looking at. So here, for example, this is one that's like sort of self-modifying code. It's not exactly self-modifying, but what it does is it calculates something and then it calls EAX. So it takes a value here, and then it adds another value, and then it calls that address. So I do not know where this call is going. It will depend on the value of those registers at that point. So that's pretty annoying. And if it was a disassembler, I would somehow have to try to figure out what those registers are. But here it's easy. I just put a breakpoint here, run it to that point, and then I look to see what's in EAX. Now I'll find out where it's going. So here's one that calculates a file name and then creates the file. This is a common part of ransomware and a lot of malware, that it doesn't use fixed file names. It randomly generates file names and domain names and stuff. So here it's going to add a .txt to some kind of file, and then it's going to have a file name down here, and then do a create file. So again, the actual file name is not hard-coded and available in strings. It's somehow generated here, and I don't really need to figure out exactly how they generate it. I just need to notice down here they create the file, so I could just put a breakpoint there, run it, and then look right here at these parameters. They're just going to be sitting on the stack, and I'll see what they came up with for a file name. So that's one of the many examples. Now here's what WinDebug looks like, and we'll be using it later. It's one of these weird things where you have a line here to type into, like a chat window, and then you have the results here. It's in a window, but it might as well be a command line tool, and you have to learn these 2 or 3 or 1 letter commands to execute, and then the results show up here. So it's really, it's not much fun, but it's more powerful. So that a lot of the real pros use WinDebug and they sneer at things like Ollie and say that's for wimps. But we're wimps right now, at least I am. When you're a wimp, you start with Ollie, and then maybe someday you graduate to WinDebug. We'll use WinDebug a little bit, but it's harder to use. All right, so suppose malware sends encrypted network data. It's the same issue. It's going to somehow scramble the data. So rather than figure out how to descramble it, you could just put a breakpoint where it's ready to go out and see what it is. This is why if you wanted to steal passwords from somebody, just typing them in a browser, and then they're going to send it over HTTPS. If you get the network traffic, you've got a problem because you don't have the key. So it's a whole lot better to run something like a keylogger on the machine where you steal the key presses before they get encrypted. It's the same kind of issue. Anyway, so here's a breakpoint to view data before that. So here it's going to get data, then it's going to encrypt data, then it's going to send it over the network. So all I have to do is put a breakpoint here where it got the data and before it encrypted it, and I'll find the data sitting in memory. So that's the game. And so here's Ollie debug, and we're going to use it quite a bit later, but here's the basics layout. Over here, you've got the addresses. Here's the addresses marching forward. Here's the actual hexadecimal instructions. And here's the assembly language instructions, things like push and call and move and so on. And then here's a summary of the calls of API calls. So this is the red things are Microsoft API calls, get version, get module handle. So you can just get a pretty good idea what's going on just by reading the part that stands out in red to orient yourself, and then only try to read this assembly if you have to when you're near the part that's interesting. Here's the state of the processor. Here's all the registers, EAX, EB, C, and D, stack pointer and base pointer. And here's the instruction pointer in red. So, and not only does it give you the address, it tells you where it is. This is inside PuTTY, this is inside PuTTY, this is in the kernel. It tells you if one of these points to something. Down here, you've got the stack. These are the words, 4 bytes at a time, 32-bit words, give it the addresses, and it even shows you what those addresses point to, if it can understand what they're pointing to. And over here, you got a place where you can dump any part of memory in hex. You'll just get addresses, hex dump, and ASCII. So anything, memory, code, strings, whatever you want to look at in detail, you can dump down there. So that's the layout of this. And you run the program right here with the run button. So you can launch, right now the program is paused, and when you want it to run, you run it here. And you can put breakpoints in and stop it. You can restart it and so on. So this is, we're going to do that later. It's great fun. So breakpoints are the most powerful feature of debuggers, though there wouldn't be much use if you couldn't stop programs partway through. So there's 3 kinds of breakpoints: software, hardware, and conditional. Software breakpoints are by far the most common, and it's really the only kind I've ever used. All the rest are only for exotic situations I've never dealt with. Software breakpoints are incredibly simple. You write this byte, CC, on the code. It puts that in the code, and it saves the byte that should have been there someplace in memory. So now it's modified the program. A CC is int3. Int3 raises an interrupt, and the debugger catches the interrupt and stops the code. So all it does is wherever you want to stop, I put a mark, and it stops there. Just like putting a nail in a track for a model railroad car. So that's the game. You get a breakpoint X, now it generates an exception, and that goes back to the debugger. So if you were to look in memory, the debugger would tell you that this instruction is 55, which is push EBP. But if you actually were to use a memory dump tool, you'd find that there's really a CC there because there's a breakpoint there. So it is kind of funny. Anyway, that's how it works. And so when you'll have a software execution breakpoint. Now, sometimes it's going to make trouble. For example, if some other part of the code changes the value at that memory address, it's going to overwrite your breakpoint, and then the break won't happen. If some other code might read the memory and find the wrong value there, like it might do something like verify a hash value or a CRC32 to make sure the program hasn't been modified. And of course, the program has been modified. So it'll now detect it as an altered program. So, you know, nothing's perfect. And I've seen that kind of thing when doing Android apps, but I've never had to deal with it in x86 code yet. Now, there are hardware execution breakpoints. There's debug registers in the processor designed to put breakpoints without modifying the code at all. There's only 4 of them, and you can do that. You can break on access or execution. So that is the solution if you have one of those problems described in the previous slide where you cannot use a software execution breakpoint. And there are limitations, like for your code could then change those registers to stop the debugger. So there is a flag to cause a breakpoint if you try to mess with the registers. So it is possible to resist that, but it's not perfect. None of these security things are ever perfect. There's always a security product, and there's always some kind of attack that will confuse it. So That's why you all have to have a lot of tools, and you have to remember that none of your tools are very reliable. They can all be fooled, but most of the time they tell you the truth. So a conditional breakpoint is a software inside the debugger. It runs software. You want to break only if a condition is true. Like set a breakpoint on this get address function, but only if the parameter being passed is in a certain list. So every time it reaches this point in the code, so the way this is done is it puts a software breakpoint there, so that every time the program hits that code, your x86 assembly stops and it jumps back to the Python, which is what your debugger is typically running in, and then the Python checks to see if it really wants to break, and if it's not going to break, it starts running it again. So it really is the debugger working in tandem with the breakpoint to do it, and that means it slows you down greatly because you jump from the fast x86 assembly language into the slow Python every time. So a conditional breakpoint will slow down your code quite a bit. Anyway, that's a thing to know. Again, these are exotic and I've never used them, but they're available in that case. All right, so I got another one of these, 8B. This. All right, good. Got 26. Good, so got pretty much everybody. Give it just a few more seconds. Okay, good. Wait a little bit more. All right. All right, so what kind of breakpoint uses interrupt 3? That's a software execution breakpoint. It will stop if it executes that byte. If you're trying to put it in something like a data section, it won't have any effect. All right. All right, what kind of breakpoint may slow down your program? It's a conditional breakpoint because it jumps from assembly into Python, which is much slower. All right, what's the most common kind of breakpoint? Software execution, the only kind I ever use. All right, which one might miss important functionality? All right, that's step over. It does, of course, mean that some code zips right past and you might miss something. All right, so we've got Ollie, who I know who that is, good. And Peter, okay. Lars again, okay. So it's been an hour, so I'm gonna stop and take a little break. Say 10 minutes, we'll pick up at 10 after 7.